I'm Docent Vicki at Point Lobos State Natural Reserve here in Carmel, California. And this is Docent Ed. Ed, what are we going to be talking about today?
I thought we would talk about reading. Reading rocks. And rocks are kind of like books. Books have chapters that tell you what was going on over a period of time. So do rocks. We're going to see some of that. We're going to see some chapters in these rocks. But books also have pages. And if you want to know what's going on at any one time, you have to read a page. But if you want to know what's happening through time, the story, you have to look at a whole bunch of pages. So we're going to be looking at chapters, we're going to be looking at pages, and we're going to be looking at sets of pages that tell us what was going on the floor of a submarine canyon thousands of feet below the surface of the sea about 50 million years ago.
So we get to read the rocks to find out what happened at that point in time, that page in history.
That's right.
Oh boy, where do we look first, Ed?
Well, we can start with these rocks right in front of us. So if we look at the rock right here, it tells us what was going on at any one time. Over right here, if we look at this rock right here, it tells us a whole lot about what was happening. And there were animals that lived in the mud. The dark material was mud, and there were animals that lived in it. Look at this tube.
Wow.
And these are open tubes that an animal lived in. And here, a bigger animal crawled through the sand and mud and mixed them all up as it went. We don't know what that animal was. Mostly we don't know the kind of animals that made these traces or trails in the rocks, but we know they were there, and we can make some guesses as to what kind of animals they were. So that's the story of looking right down on one page. But if we want to look at what happens through time, we want to see the history, then we have to look at a set of rocks. So as we come up, we've got lots of light-colored sand with all sorts of traces in it made by animals. Over here is a beautiful one. But as we go this way, the sand gets less and less and less. That's history. That's almost a chapter in itself, a little chapter, as we go in this submarine canyon where these rocks formed. And in this particular period of time, this chapter tells us of a time when we were getting sand flows coming through pretty commonly, but not so commonly that animals couldn't make burrows and passageways through the sand. But by the time we get up there, a little bit higher in the section, where the sands get thinner and thinner, and then they just disappeared. Those light-colored streaks are all sandstone beds, and you can see they just sort of vanish as we get up there. And what that says is that this was a time when we were getting sand coming in and less sand, and then it got very, very quiet in the submarine canyon.
Yeah, so Ed, you're right. Looking at these different layers of rock, a series of them, is just like reading a book. If you can read the layers and the things happening in the rocks, it's like reading a book. That is so exciting. I didn't know you can read the rocks like that. So we challenge you to go out and find some layered rocks in your neighborhood. Tell us the story. Write and draw some chapters. What do the rocks tell you? You read the rocks. Let us know what you find, and come and visit us here at Point Lobos State Natural Reserve in Carmel, California.
Vicki, Ed, fabulous. And isn't it wonderful that my video's not on, sorry, everyone. Fabulous video, and it's wonderful that that our school children are getting exposed at such an early age to such wonderful information, our next generation of young environmentalists. So we're really proud to have you sharing with them. So thank you so much. And I introduced to you, if you don't know, Ed Clifton. He's a current Point Lobos docent, former PLF president, and a retired geologist. And Vicki Odello, who's with us, she's a Point Lobos docent and a consulting geotechnical engineer. That's a mouthful of a title, but thanks to both of you for being here and sharing your knowledge, and I'll let you all take over from here. Thanks so much.
Are you ready for me?
Whenever you're ready, we're ready.
Okay.
Yes.
All right. Well, I'm going to talk about a love affair since it's just a little past Valentine's Day, but it's a love affair of rocks, specifically the rocks of Point Lobos. And let's see, I need to advance that, and my advancer, let's try this. There we go. Okay, so just a few years before I ever saw the rocks at Point Lobos, as an undergraduate at the Ohio State University, I was taught that all sandstone and conglomerate originated in shallow water, basically because prior to the 1950s, geologists thought there was no mechanism that could transport sand into deep water. But in the mid-50s, there were some European geologists who were making some marvelous experiments where they had a tank of water with a sloping base, a sloping floor to it. And on that sloping floor, they poured a mixture of sand, mud, and water. And as they expected, it just went, the mud water mixture just poured down that slope. And they call this a turbidity current. And probably it's analogous to a snow avalanche coming down a mountainside. And these are capable of transporting, we know now, great amounts of sand into the deep ocean. And they have a distinctive deposit because as the current loses its energy, the largest particles it's carrying drop out first, and they're followed by smaller and smaller particles. So what you get is a bed that's graded coarse at the bottom and fine at the top. And so this is a characteristic feature, almost diagnostic feature of deep water sandstones. So a short time later in the early 1960s, when I started graduate work at the Johns Hopkins University in Baltimore, deep water sandstones were really a hot topic at that time. And there was a lot of work being done on them. And every now and then there would be a paper that would talk about coarse-grained deep water deposits. And that really resonated with me because my thesis was on a very strange coarse-grained rock in Nova Scotia. It looked kind of like this. This is not that rock. This is from Angola. But it was a very rubbly, very, very strange rock. And I found out that it had been produced by the collapse of caves in a broad area some tens of millions of years ago in Nova Scotia. And so I was really turned on by these coarse-grained rocks. And if I'd had a chance to work on anything, I would have loved to have worked on deep water coarse-grained rocks. But when I graduated, I immediately joined the U.S. Geological Survey in Menlo Park. And my first assignment was not the deep water deposits, but the shoreline, sandstone and conglomerate that were beautifully exposed in the Caliente Range and the southern coast ranges. And that work pretty much shaped my career for quite some time. Well, back in 1965, my parents flew out from Ohio and we decided that we would go on a long weekend trip to the Monterey Peninsula, which Sunset Magazine said was really a great place. And it turned out Sunset Magazine was right. And while driving down Highway 1, I saw this sign. I thought, well, I wonder what that is. So I went in and paid $2, I think, and drove out to the coast. And there was this amazing set of rocks called the CARMELO Formation. And looking at them right away, you could see that they were composed of graded sandstones. These were a deep water deposit, the result of turbidity currents. And there were conglomerates, lots of conglomerates. And I thought, aha, here's my chance to study deep water conglomerate. But turned out there was a graduate student at UCLA who was just started a master's thesis on the rocks of Point Lobos. And geologic protocol is you just don't barge in on somebody else who's working in an area. You let them finish up and maybe get a chance to publish it, and then you can go in. And so I stayed away from the rocks of Point Lobos for some time and instead devoted myself to working on coastal problems. And I was able to use the new technique, relatively new technique of scuba to go places geologists had never gone before and see things they'd never seen before, like the floor of an active surf zone in Oregon, or the floor of a tidal river in coastal Washington. And that underwater research led me in another direction, which was participating in a Man in the Sea program, where I spent 80 days of living and working from an undersea habitat in the warm waters of the Caribbean. And 60 of those days were in one continuous stretch. So that was how I was spending my time. Occasionally I'd get back to Point Lobos if somebody was visiting from afar, visiting scientist who was interested in that kind of rocks, but otherwise didn't really spend much time there. But that changed in 1978 because I was asked to take on an administrative position heading up the branch of Pacific Marine Geology. And it was a huge branch. We had 3 seagoing vessels we were trying to maintain and operate. And I was dealing with all sorts of things that I'd never had to deal with before, like problems with the Maritime Union and navigational systems that were breaking down, and trying to keep the complex geophysical data collecting system working, and personnel problems and budget issues, and on and on and on. And I rather quickly decided I needed an escape hatch. I needed a place I could go every now and then just to work on the rocks. It had to be within a couple hours away, close enough I could get there in a reasonable amount of time, but far enough away I couldn't be dragged back. And mercifully, this was before the advent of cell phones. And I thought, Point Lobos is just about the right spot for this. And so I started spending long weekends, coming down on a Friday morning and spending Friday, Saturday, and Sunday working on the rocks, then going back recharged and ready to take on my administrative responsibilities the following Monday. And in doing that work, I found something that people hadn't noted before, and that was we're really dealing with deposition in a submarine canyon. And something sort of akin to the upper reaches of Monterey Submarine Canyon, the modern canyon that crosses Monterey Bay. Now that canyon and its associated canyons have absolutely nothing to do with a fossil submarine canyon at Point Lobos. It formed probably 50 to 55 million years ago, way to the south, perhaps even as far south as northern Mexico. And so why did I think it was a canyon? Well, if you looked at the contact, the boundary between the CARMELO Formation, the conglomerate that you see there, the brown, and the gray rocks to the left, which are granitic rocks, they're the basement of this whole area. You can see that's kind of a steep wall. That's not a flat surface. It's actually a wall. And that wall could be traced across the northern part of the reserve It's exposed again in Headland Cove. We'll look at it over from Sea Lion Point and up a bit closer. And again, you can see it's a steep wall against which the conglomerate sandstone of the Carmelo Formation are plastered. To the south, the contact comes ashore at Hidden Beach, which is aptly named because I don't think, as far as I know, nobody's ever really seen the contact there. It's buried beneath the beach sand on the beach and in the rubble at the back of the cliff, and I certainly have never seen it, but it has been traced up into the hills beyond the shoreline, where it gets up to about 250 feet. And that information allowed me to put together a cross-section. We don't know how far down the Carmelo Formation extended, but we had at least some idea of the dimensions, which we then could compare to what we thought were similar water depths in Carmel Canyon just to the north. Again, no connection between that canyon and the ancient canyon at Point Lobos. And looking at those cross sections, it turns out that they're actually pretty similar, which doesn't prove anything, but it doesn't disprove anything either. So it allowed us to go ahead with the idea that this was a submarine canyon. There was one other piece of information that was useful, and that was the orientation of pebbles in the conglomerate. Pebbles that are moved by flowing water are shingled, and they take on it's called imbrication, but shingling is a good term, and you could see that there are quite a few pebbles in that gravel bar that are parallel to that white dashed line. And this is characteristic of pebbles moved by flowing water, and it tells you the direction in which the water was flowing. And so looking at the conglomerates, yeah, we could see that kind of shingling in the conglomerates. If you look at the long axes of the pebbles, they are around that dashed line.
Yeah.
You see they're pretty much parallel to the dashed line. And so putting together the direction of flow, that seemed to indicate currents passing directly through the submarine canyon. So the Carmelo Formation then, we thought, accumulated in a submarine canyon. And geologists started coming here from all over the world to look at it. So what were the processes that filled that canyon? That was the second question. And we noted that the sandstones are graded, and but there's a lot of conglomerate. And how did all of that conglomerate get down into the deep water of the canyon? Well, some of it was kind of easy, because if you had a conglomerate that was all messed up and disorganized and no internal organization at all, you could explain that as a debris flow or submarine landslide that probably was associated with the turbidity current that moved down the slope and into the canyon and was deposited there. But there were also lots of conglomerates that were too well organized to be explained by a submarine debris flow. And this then became the next focus of research. Now the sandstones show normal grading, coarse at the base, fine at the top. And one of the things we found was that conglomerates, characteristically, when they were in beds, showed just the opposite. They were fine at the bottom and coarse at the top. How did that happen? And it's something we just saw over and over again. It's a common signature in the bedded conglomerates at Point Lobos. So how is this inverse grading produced? Well, one place it's produced that's been known for a while is on the slip faces of sand dunes, where the grains cascade down the slope, and the jostling of the grains, the collisions, but keeps them from settling out, and the biggest ones go up to the top. And so you get inverse grading in the layering that are produced by these kinds of dry flows down a dune face. And this is a characteristic of sand dunes, ancient sand dunes, when they're found in the rock record are these inversely graded layers, but they require, a steep slope down which the sand or gravel can flow. And the seafloor at Point Lobos had a gentle gradient. It was not steep. So how did these deposits accumulate? Well, another possibility was a modified grain flow in which a moving current drove a dense concentration of jostling grains, and the coarser grains moved up within this, producing an inversely graded bed. And I discovered this initially working on beaches in Southern Oregon, where the backwash of a beach carries a moving bed of sand, and that bed of sand characteristically is inversely graded. Coarse at the top, and fine at the bottom and coarse at the top. And so that seemed to be what was going on with these inversely graded gravels. But there was another problem, and that was in the sand, there were floating boulders, just the largest class in the deposit typically ended up just floating in the sandstone. How in the world did that happen? Well, looking at their orientation and the flow direction, which we got from the imbrication of the pebbles, what we found was that they occurred with their long axes perpendicular to the flow. And this is something you get with rolling pebbles that are moved by a current, rolled along by a current, is this orientation is perpendicular to that flow. And so what we're seeing here is the fabric is showing us that the long axes were perpendicular, transverse to that flow direction, and rolled along by the sand. So the model I came up with is we have a turbidity current, it's a big one, and down at the bottom, gravel grain flow driven by that turbidity current that's moving it down the slope. And when it comes to a stop, the sand keeps right on going. The sand flow keeps right on going and strips pebbles off the top of the conglomerate layer, the gravel layer. And these are the biggest pebbles in the gravel layer because it's inversely graded, and it carries those out and deposits them along within the sand. This is the same thing basically shown by somebody who was a much better artist than I am, but I think you get the idea of the passage of these turbidity currents leaving behind these masses of gravel as they pass through the area. So we had at that point figured out pretty much that we were in a submarine canyon, and we had some ideas about the origin of the organized conglomerates. And during that period of time, I led field trips here, wrote several papers on it, and then retired from the survey in 1991 and took a job with Conoco. Today it's ConocoPhillips, and I was sort of an internal consultant, but I got to lead a few field trips to Point Lobos, but that was basically my only connection during that period of time. But then I retired from Conoco in 1999 and returned to the Bay Area where we kept our house. And in a couple of years, we made the move to Monterey, which had been in our plans for a long time. And I became a Point Lobos docent and started a second chapter to my study of the Point Lobos geology. During the years, there have been a number of papers that tried to describe the organization of the rock types in the CARMELO Formation to use as a model for deposition in a submarine canyon. I tried this myself. I wasn't very successful. And these are all kind of different. They're not similar, and they're not altogether convincing. And I discovered why, I think, because as I was leading field trips with Point Lobos docents and aquarium volunteers to Point Lobos in the early part of the 20th century, 21st century, I noted that in the northeast part, the pit and Moss Cove particularly, there were some strange features in the rocks. Moss Cove particularly was of interest because it seemed to be sort of a little tributary canyon coming off of the main canyon, and a good exposure of the wall of the canyon and the sediment that accumulated directly on the wall. So over to the right, I've got my left and right, I am dyslexic as all get out. Anyway, over on the side by where B is, if you can see A, that is the granodiorite, the crystalline rock that forms the base. And then sitting on top of that is conglomerate. And the conglomerate gets muddier and finally culminates in a pebbly mudstone, which is just mudstone with scattered pebbles in it, then a sharp contact, and over that is sandstone, is conglomerate, and then sandstone and conglomerate. And you could see a little more closely in this sort of fuzzy picture of the contact between the pebbly mudstone down the lowest one with the yellow dashed line. And then on top of that, we have the accumulation of sand conglomerate and sandstone and conglomerate in the beds above. And they're at a different angle. They're at a lower angle. They're dipping more gently than that steep one, that's the steep contact down near the bottom. And this shows it again, sort of on a broader scale. And what it looks like to me is that you had a landslide that came down the slope of the granodiorite, sitting on the granodiorite, piling up in this unstratified conglomerate that culminates in a pebbly mudstone. And then that is preserved as it's filled in from the other side by the organized conglomerate that is got more gentle inclinations. And this presents a problem because what it looks like is that the conglomerate slid down from the wall into some empty space. Well, what was the conglomerate doing up on the wall when there was empty space down below? Across the way is the pit, and the pit is another good exposure of the contact, one we saw before. And here you can see there are large lobes of this brownish material that are coming down into the gray material. And what these are just giant slides of conglomerate that are pushing down and bulging into the underlying grayish muddy sediment. And again, what it was telling us was that gravel was sliding down from above into open space in the canyon floor. So why was the conglomerate perched up on the wall? Why did we have space there? And the only way I could explain this was the canyon had filled or partially filled, and then suddenly there was a partial evacuation, and you got the sidewall slumping coming in from the sides of conglomerate down into this new cavity. Well, it's hard enough to fill a submarine canyon. Emptying it is really hard. How in the world do you do that? And it was then I started focusing on the south shore, the other canyon wall, and where I'm convinced that there is a piling up of large blocks. And you get a sense of how complex the geology is over there by looking at this stretch south of Sand Hill Cove down to just about the Piney Woods picnic area. And this is a view looking back from the air. And you can see it's a pretty complex situation. Actually, it's really complex. And we're going to focus in on a couple of things here. Up near the top, that gray line that goes across as a streak is a muddy slide surface on which the beds above have nothing to do with the beds below. And on the right-hand side, is the muddy beds, and to the left, conglomerate. And if we look at that in detail, you can see, and they're both sitting on top of a slide plane that totally disconnects them from the underlying beds. And you can see that the contact between the conglomerate, CGL, and the mudstone, MDS, isn't a straightforward contact. It's just kind of they're mushed against one another. They were crushed against one another while the deposit was still unconsolidated. It had not turned to rock. If we look down below to the beds below that, there is an absolute mess in the sandstone and mudstone below this. And you can see it here. The sandstone is buckled, shoved up over itself, it looks like. You couldn't do this if the rocks were brittle as they are today, fully consolidated. They'd break up into fragments. But these were dragged around. They're twisted, contorted. They weren't fully consolidated at the time. And you see this repeatedly along the South Shore. This is a beach just south of Weston Beach. And in the upper part, you can see where the people are standing. It's almost a continuous section as you go across from conglomerate, which is the dark rock, to the thick bedded sands, to thinner bedded sands, until finally getting towards the edge on the right, you get mudstone. So it's just pretty much a straightforward system. But then you have this funny block that the arrow is pointing to. And that block has to wedge into the space in that that straightforward upwards fining section that you have with the people on it. And when you look at features in the block, again, the beds, the material flowed. It was not yet consolidated into rock when this happened. And you see this over and over again in different places along the South Shore, where you get boundaries between large blocks of sediment. And apparently the sediment was not fully consolidated into rock at the time that happened. This is just to show you how geologists portray the orientation of the inclined strata, because it bears on a slide that's coming up. But essentially, we have what we call strike, which is the line that is made by the intersection of an inclined layer and a horizontal surface. And the dip is just the angle which it is dips off in that direction. And looking at the South Shore, you can see lots of strikes and dips, the symbols along the South Shore in that lower diagram. And what I found was that you could break these into segments. And typically there was a boundary, a sheer boundary between these different colored blocks. And you'll notice in some places, the beds are dipping offshore, and the next block over, they're dipping alongshore. And they're just all kinds of variations that occur within these blocks. So I think what we have is a set of massive slide blocks, partially consolidated. It wasn't rock at the time, but it'd been buried for a while, and it slid down the slope and accumulated against the canyon wall, which runs along just a few hundred meters offshore. I gave a talk to the Point Lobos docents on the geology of the Big Sur coast last year, and while I was putting it together, I was looking at the Google Earth offshore topography, the seafloor topography, and I found this curious feature just south of Lucia. It is, looking at it, it looks like just a series of giant blocks that have slid down onto the wall of a submarine canyon. Now, I don't know if this is real, because I don't know how Google Earth puts together their information. Sometimes I think it's really good. Other times it's probably a lot of imagination goes into it. So I don't really know if this is a true feature or an artistic effect. But it's what I think happened in the canyon at Point Lobos. And if we take that particular canyon south of Lucia and plot it the same scale of Point Lobos, well, my goodness, it kind of looks like the same thing. Again, I'm not sure that the one, the Google Earth one is real, but it does show what I think happened in the deposits at Point Lobos. So that's why I love the rocks at Point Lobos. Thank you.
Oh, thank you so much, Ed. That was wonderful. Oh my gosh, I think I have to watch that a few times to absorb it all. Welcome
There we
back,
go.
everyone. Well, I'll open it up to any questions. If you do have a question, you could either put it in chat or what's the best way to do it? I think we could probably manage to ask questions one by one. Feel free to chime in. Everyone can unmute if you want.
Is anybody awake yet?
So I had a question about just the sandstone itself on the South Shore, where the big circles are embedded in the sandstone. Can you explain those, how those come about?
Yeah, those
Oh,
are
lovely talk, by the way. It was just wonderful. Just very exciting. I can't wait to go back out and look at all that stuff that I've ignored before.
well, thank you.
Thank you,
Yeah.
Dennis.
Yeah, those things are called concretions, and they're masses of sandstone typically that get cemented before the rest of the rock for some reason, and just giant balls. And then the rest of the rock is consolidated around them. And sometimes they pop out. There are zones of differing degrees of resistance to weathering and erosion. And sometimes they pop out and leave holes. Sometimes they're just big balls that sit on the surface. If you go to the Point Lobos website, the foundation website, and check out the geology section, there's a little publication in there that talks about these and some of the other weird features that you see in the rocks at Point Lobos.
Does that help, Dennis?
Yes, thank you. Since I'm just going to ask another question then. It's about the time frame that you think these slides and turbulent flows happen. You alluded at the beginning of the talk to the idea, which I heard before, that the granitic base had actually migrated up the coast from Mexico. When do you think that these interfaces between the conglomerates and sandstone and the granitic base happened? And any ideas about when perhaps this undersea slide might have happened in geologic time?
Yeah, first of all, that's a really good and complex question. And the rocks themselves, the Carmelo Formation, probably formed in northern Mexico. This, I don't know if Tanya Atwater is in the group, but I saw her name here at one point. She is the guru of Central California geology, and I use her work a lot. It's amazing stuff. And she has been able to show that the plate motions are such that we really didn't start moving anything to the north probably until about 18 to 20 million years ago. And so all of these rocks are older, and they were not involved in that movement until much more recently. So the features, all of the features you find in the Carmelo Formation, the concretions, the trace fossils, the graded beds, everything that you see there that formed in that canyon, all formed probably northern Mexico is my guess. And plate motions eventually were such that that particular chunk of rock, of coast, got attached to the Pacific plate, which is the one we have offshore now, and which is moving north, and they got moved up here from Mexico, attached to that plate.
Great. Ed, Todd asks, is a conglomerate landslide heavy enough to displace underlying mud prior to if forming mudstone?
Say that again.
Is a conglomerate landslide heavy enough to displace underlying mud if prior to forming mudstone?
I would guess so, yeah. I would think that any of those landslides, in fact, the turbidity currents probably had an erosional capability of stripping off. If there had been mud accumulated on the seafloor before they arrived, it almost certainly would have been stripped away, and maybe some of the sand. So there's probably a fair amount of just missing section or missing sedimentary rock that was sediment at the time that was stripped away as these currents moved down through the canyon.
Interesting. And hi, Don. He asks, how do you account for twisting and folding of CARMELO formation through the plate tectonics as it relates to the formation's orientation that we see now?
Actually, I don't think, if I'm right, I don't think that the attitude, the orientation of the beds at Point Lobos really have very much to do with plate tectonics, that they probably moved as an intact mass. If you're inside the conglomerate forms kind of a nest, and granite, the granitic rock. Let me back up and start over again. Untie my tongue and get going. The conglomerate and sandstone sit in I think of it as a nest. If it's a submarine canyon, that's a very strong rock. The granodiorite doesn't bend easily. It breaks, but it doesn't bend very much. And I think they were probably pretty well protected in that during the subsequent motions. There could certainly be tilting, there could be some faulting and breaking, and there is evidence that there are some faults that are fairly late in their development that probably do reflect movements associated with the plate motions. But I think most of what we see there probably occurred, most of the attitudes of the beds occurred before the arrival of the Pacific plate that started everything moving north.
Wow.
I have another one if you'll take it.
Sure.
So we think that the granodiorite was formed about the same time as the whole Sierra Nevada range. Is that correct?
I haven't really dug into that, but I'm guessing it's probably close. Yeah.
So that, and we know that that granodiorite was clearly unroofed from its formation underneath the earth by the time the CARMELO formation was laid down in 50 or so, 60 million years ago, right?
Right.
Because I know there's a lot of debate about how long it took to Sierra to get unroofed, and a lot of the estimates are way later than that. But
Yeah,
CARMELO tells us that it must have happened relatively quickly.
Yeah, and again, we're far enough south that I'm not sure that we're really part of the Sierra complex.
Okay. So it could have its independent development.
Yeah.
But obviously it had been, whatever, I forget, 8-10 miles underground when it was formed, and then.
Yeah, that's one of the to me, one of the real mysteries is how and when and why did that rock move up to the surface? Because it had to move a long way. And there was something that happened, and I didn't see anything in the plate tectonics record that would suggest that there was an event that would cause it. And the only thing that happened during that time, 65 million years ago, you had this huge impact of a small asteroid on the Yucatan Peninsula. But I don't really, the time is right, but I don't really think it would have the capability of shifting the rocks around to that extent on the West Coast. I think it has to be plate motion somehow.
Thank you.
Thanks, Todd. That was great. Appreciate your questions. It's important. Does
Yep,
anyone else
great
have
questions.
Yeah, really great questions. Does anyone else have any?
You do have one, Tracy, in chat.
Oh, great. Oh, thank you. Okay, thank you very much. Are there any underwater geological research going on, or is there any underwater geological research going on currently around Point Lobos? If so, what depths are the researching at?
I think the only underwater research around Point Lobos in recent years has been done by the Monterey Bay Divers Association, who have put together some remarkable maps of the seafloor. And at the at Whalers Cove in the parking lot, there's a model that we have that they helped put together. In fact, they may have done the whole thing that shows the seafloor, but they have done some marvelous work on just mapping the bathymetry off Point Lobos. But as far as I know, there has been no further offshore research done in years down here.
Right, and I'll chime in a future event, virtual event, we'll be talking about the mapping that occurred on the seafloor and some continuing work that's building on that research. So that'll be a really, really fascinating event as well. So we'll be talking about that in the next couple of months. Please, anyone else, just chime in. Don't be shy.
So I'll keep asking. You talk about the turbidity currents, which must be pretty powerful. Where do they come from? Is that ocean currents? Are they related to tidal flows, or are they terrestrial river-like sources?
My guess is they are probably triggered. They could be triggered by big floods at the mouths of rivers, building out a lot of sediment that cuts loose and produces a large turbidity current. They could be produced by earthquakes. My guess is that significant earthquakes can generate turbidity currents all along a coast. And I think they're probably too deep to be, well, a tsunami, if it roiled up enough sediment in the water, could generate a turbidity current. I wouldn't think it would be a particularly large one, but I don't really know.
So since there are multiple layers, this must be a recurring phenomenon?
Yeah, when you get sets of layers, it's just one after another piling up, carrying sand, gravel in the case of Point Lobos, down into the deep water. Floods would certainly be a major factor. I think probably floods and earthquakes in the deposits at Point Lobos.
And Ed, can you tell the interval between these multiple events?
No, don't really have that kind of timing, time capability.
Muted myself. Vicki, before we wrap up, Could you touch briefly on the work that the Youth Programs Committee does to make the quick videos that I showed in the intro?
Oh, sure. Yeah, it's quite a team. When Ed and I are being filmed, there's about 6 or 7 people on the other side of the camera. And it's quite a team, and they do many videos and pre-production, prep production, filming, and a lot of post-production. And the team puts these together for tide pools, several geology ones, and several others. And then they prepare them for the school, which has to meet a certain criteria for them to be even accepted for the school program.
It's wonderful work. And I thank all of you, because all of your support of the foundation makes those videos possible. The equipment purchase, all of the hard work that goes into it. It takes a lot of effort. And Don, I'll thank you because I can see you. Thank you and the Elks for such a generous grant that really has really benefited the school program there and the videos. They were able to purchase really important equipment. So I want to just take a moment and really call out and thank you for that. Do we have any other questions before we wrap up today? I want to say I appreciate everyone being here, and I really appreciate, Ed, you taking all the time to really, bring us this information that's so fascinating and they're so deep. I think I have to watch this a few more times to to really grasp it. I've told you that before, but it's always something new that I pick up from it, and I'm sure everyone feels that same way. But any other questions, though? I don't want to leave anyone out.
Well, for more fun, Ed, I saw one of your last slides was your empty soda bottle filled with different graded rocks. Did you want to explain that video for any diehards here? Maybe go back to that. That's a little
Let's see
experiment.
if I can find it. I had it in as part of the talk and then thought, well, it's getting kind of long and I probably can explain it without showing that. But let me see if I can go back to screen share and go to this one. Oh, and there it is. Yeah, can you see this? Is it coming through?
Yes, it is.
Okay. Oh, try this. There we go.
Perfect.
Yeah, this is something I've been doing for particularly training of docents, and how the accumulation from turbidity currents as well as the rain flow produces grading and inverse grading. And I use a sand and gravel, fine pebbles, in a bottle. And let me, for some reason, it's going forward, and I don't want it to go forward. There we are. So you just mix them up, shake everything, put them in suspension, and just let them sit. And there is a normally graded bed. Or you can take that same bottle, same sediment in it, and you can shake it up so everything again is all mixed up, and then just jostle it so that the bottom sediment is moving back and forth, but it's not really going up into the water. And you watch, and the pebbles, the coarser grains, go up to the top, and the sand goes down to the bottom. You can see that, I think, here in the one in the bottle, the sand along the bottom and then gravel at the top. This is a great way to demonstrate how graded beds and inversely graded beds are made. That come
Awesome.
through?
Thanks, Ed. That was great.
Yeah, it is. Looks like a fun thing to try at home. Oh, that's great. Well, thank you all so much. And if you have any, if you get home, you're home, if during the day, a question pops into your head, or there was a question that you didn't get to ask, or for any reason, please shoot me an email. I will connect you to Ed and Vicki, and we can get all your answers, all your questions answered. And as usual, this is a recorded, so anything that you missed, you can review. I'll send it out, and you can share it with someone you feel would enjoy it. Please do. Please always do that. Feel free to share it with people you love and will enjoy it.